All right, so that's the Fibonacci stuff, and that's the rotating stuff. All right, so when I was doing this, I was thinking I should add the greens on here, but for anyone, you can sort of calculate what the greens are, and I guess we just if you ignore the 2, then 4 is perfectly balanced, and 7 has height 2 over here and 1 over here, so it's off by 1, right? Now, if we insert the 2, then what they're saying is remember how you insert something? You walk down the tree looking for it, and where should it be? It should be on the left of 3, but left of 3 was the empty tree, so we put it there, right? And then you can, if you either do it recursively or have back pointers to parents. It's nice to have pointers to parents, right? If you have pointers to parents from 2, you can walk back up the tree to get to 7, right? And as we walk up, we can say, right? We can say, hey, Mr. 3, we made your left tree 1 bigger, right? And Mr. 3 says, you know, I was labeled 0 because my left and right were balanced. And if you make my left bigger, then I go from a label of 0 to a label of 1, and I don't mind that, so I'm happy, right? He changes his label from 0 to 1, and he's happy, right? Then we go up to 4 and say, hey, 4, how do you feel about making your left 1 bigger, right? And without the 2, he's also balanced, right? He's got 1 on the left and 1 on the right. So he has a label of 0. And when you make the left 1 bigger, he changes his label to 1, right? 2 minus 1, right? And he's happy, right? And then you go up to 7, and you say, hey, 7, how are you feeling, right? 7 was saying, well, I'm labeled 1. That means my left child was of length 2. There was already a difference of 1, right? 2 minus 1, there's already a difference. So she says, I'm upset, right? Because now if you make my left 1 bigger, then my imbalancedness is 2, right? Which isn't allowed, right? Everybody get that? So you walk up the tree until you find the first problem, right? And the way I'm labeling it is that edge between, right? 7's the first problem, and so it becomes a factor of 2 instead before, and it's no longer an AVL tree. So I say focus on this edge between the 4 and the 7, right? 7's the problem, but you came from 4, right? So you want, in fact, what are we wanting to do? We're wanting to lift up the 4, and we're going to bring down the 7, right? So when we rotate it, we got 2 next. Oh, you got, that's it. We got 2 things happening at once. Kind of weird. Here we go. All right, so there's my red, right? We rotated the red edge. We found out what was hanging, and then you hang everything there, right? And then you're going to want to calculate, well, what are all the balance numbers, right? Within the 3 trees that we hung off, they're all happy, right? We know tree 2 and tree 3 are happy because we didn't touch them, right? Tree 1 is happy, remember, because we walked up and there were no problems through tree 1. right? Our first problem was when we hit kind of 4, 7 problem, right? So then we say, well, right, this guy was right, they became balanced. 4, right? 4 becomes, if you sort of kind of try it out and see that 4 becomes perfectly balanced. Does that make sense? And 7 is perfectly balanced. I guess right? I mean, we can go through the proof, but it seems from this example, it kind of works out. And in general, it works out, right? Everybody buy that? Right, so if 7 has now a 0 label and 4 has a 0 label, then do we have the, right? So that gets a 0, and this guy gets a 0, right? Now, you might say, right, everybody 4 and below is happy. What about the rest of the tree, right? There's all the parents up and stuff. Are they going to be a problem? No, they're not a problem, right? Because, another thing that we have to observe is that the height of this tree here is the same as it was before, right? I mean, this is kind of proof by picture a little bit, but before you put in node 2, this was the height, and now it's the height, right? So not only is 4 balanced, but the height that 7 was before we put the 2 in equals the height that 4 is after we add the 2 and we rotate, right? So the tree that we're looking at has the same height that we had before, right? Does that make sense? And that means everybody above us, if they had a happy balance before, they still have a happy balance because this tree didn't change its weight, right? Does that make sense? So when you're doing an insert, you walk up till you find the first difference. And of course, you could be coming up from this direction, right? If we inserted 9, then maybe we're coming up from 9 and the problem, and then 7 has the first problem. And so it's the edge from 7 to 8 that's a problem, right? And then we rotate this way, right? Does that make sense? Everybody good? Yeah? Yeah. Why was it 1 before? Yeah, so on the balance side, what um so if we were going to do a really formal proof here, which I'm not sure people want to do, we would have to say, well, if this was a balance of -2, then what's the height of T1 versus the height of T2, right? And oh no, this one was balanced, right? And you know that this had become a -1, and so this one became a 2, and so then I mean, we can work out the height of each of these trees, and it works out so that they both become perfectly balanced. I mean, you can't really see. I mean, this picture here, it looks like this is lower, but it would. But I mean, an example of the nodes are all the same height, right? And then if you had bigger trees here, then you would have to argue that it's always going to be the case. I'm not sure I'm answering your question or not. Yeah. Yeah, so this now has 4 has a left tree of height 2 and a right tree of height 2. So the difference is 0. And this guy has 1 and 1, so the difference is 0, right? And right, and why do we know that that's going to work? Is, well, we assume this guy did get bigger, so why is 4 happy? As well, because it used to have a balance of 0 and now it has a balance of 1, right? So we know this guy's balanced. So we know the heights of T1 versus T2, right? And because this now has a height of a balance of 2, we know the relative heights of these. And so it really works out to the same example. We're going to get a 0 and a 0 here, right? People kind of, right? So here's just another example, right? Here, this tree, this has a balance of 0, and this has a balance of 1, like before, right? And we add a node, and we say, hey, 5, we've just made this bigger. And 5 says, I don't mind. I'm going to become balance of -1. And 4 says, well, I was 0 before, so now I'm going to become -1, right? And 7 says, oh no, I was -1 before, and you're making me -2. No, +2, because it's still on the left, right? So he's +2. And so then you have to think about this example. And again, the problem is at 7, but we got the problem coming from 4. And so we rotate it. And then now we can see, oh, all right, so now it's not good, right? Because we still have a -2, right? Still not so that didn't work, right? So I guess I'm now remembering that there are a lot of cases, right? So here's a all right, so let's start over again and think about all the trees. All right, I guess I'm okay. I'm a little hot, but I'm okay. I personally would hate to have to memorize all these cases, right? So I think if I was actually doing it on a test and you gave me an actual tree and you'd say, oh, I do the minimal rebalance, you don't memorize all the cases. You just say, oh, what am I going to do in this concrete case that they gave me? Can I do a rotation to make it work, right? But evidently, it's all divided into these bunch of cases. It says there are 6 cases, but we've only shown in 3 of them, 4 of them. Some are probably symmetric, right? So right, right, these 2 cases. So you do a rotation and you do a rotation. I guess this guy here, you have to do. This is sort of the one that we were doing before, right? The first problem is so I guess what they're saying, how you identify these cases is you look at you look at the 3 nodes, which are right, Z, the one that's the problem, and the one that you were at before, the path coming up, and then you see what order they're in, right? So if in this case, we were coming up, we added something down here, and then X was happy and Y was happy, and we got to Z, right? And here we're coming, X was happy, Y was happy, we got to Z in the different orders, right? And so then what do you do in these various cases? Well, in this one, you rotate like that, and it worked. And this one, you have to rotate twice. In fact, oh, maybe this is, right? So we inserted something, you follow the path up, right? Then it may create an imbalance, right? And so there's the imbalance, you know, so you keep, so I'm still happy, right? So I go up and I'm still happy. So I go up and I'm still happy. So I go up and now I'm not happy, right? So that's kind of where the problem is, right? And then you find 3 nodes, right? So Z is the first guy that's not happy, right? And then who's Y is going to be the child of Z with the highest tree, right? Which is probably where you inserted it because you made it bigger, right? So here, this one's going to be Y, right? And then X is the child of Y with the biggest tree, right? So we identify, those are the last 3 that we went through, right? And I think this is maybe people before were talking about edges rotate. Let's talk about these 3, what we're going to do with these 3, right? So if we have these 3 nodes, X, Y, and Z, then, oh yeah, I'm trying to think, not doing 2 rotations, but just do it, right? So here, what do we know about these? Well, this guy, if Z has some height h, right, then one of its children has h minus 1, right, because it's 1 shorter, and then another child, right, right, so this one's the tallest, so it's going to have h minus 1, while this one's going to be shorter, right? It's going to be h minus 3, I guess, right? And then this guy's, right? Everybody good? Because these are the tallest, so those are the heights, right? And this has the imbalance, right? So it increased, so it's going to be a balance of 2, right? So that's going to have a balance of 2, and so then this guy's going to have h minus 3 height, right? Because h minus, we want h minus 1 minus h minus 3 to be 2, right? And the balance factor here, well, it could be 1 or minus 1, right, or 0. So we're gonna pretend it has 1 now. So that gives you the height of all the trees, right? And right, so you rotate that, and then you hang the guys off, and everything works out, right? That was the kind of the proof of that case that we first did, right? And the rest of the tree should be fine, right? Because the tree hasn't changed height. All right, so now in this example, remember it didn't quite work. So we follow the path up, and we see here, right? And we have our problem, and we label this guy with Z, and this one, right? We get X, Y, and Z, right? Now, This is where I say you can do two rotations, right? You can do, right? You can calculate what the height of everything is, just from our example. And then you rotate like that, and then you rotate a second time like that. Now, what I'm saying is, why rotate it twice? I'm just saying, I got this XYZ pattern, right? I want to have something that's more generic, that you can do it all in one go without thinking too many cases, without frightening people too much, right? So what are we doing? We added something. We followed the path up. Z's the guy who has the problem. Y was the guy before it. X was the guy before it, right? And so then you say, well, let's just build a tree with X, Y, and Z, right? And what order should they be? Well, they're labeled with numbers. And of X, Y, and Z, who's the smallest, right? Y is the smallest because X is bigger. X is bigger than Y and smaller than Z, right? So you can say, well, who's the guy in the middle of these three? Well, X is in the middle. So you can think about it as two rotations, or you could just build the tree with these three, right? And you can see it's a little nicer because this was imbalanced and this is balanced, right? You're just building a little balanced tree. And then you have 4 trees hanging off, right? And what do you do with those 4 trees? Well, you put them where they belong, right? Does that make sense? And when you put them where you belong, and then you have to calculate, did it work? And you calculate all the numbers and say, oh, look it worked, right? And right, so here's an example, right? We need to insert 12. So you go over from 7, you go over from 19, over from 13, over here to 11, over here to 12, right? That's where our new guy goes, right? And then those numbers, right? We change. We got numbers inside and numbers outside. What are the outside numbers for? What? Oh, is that the height? Fair enough. Oh, I see. They're not. He's storing the height of every node, right? So then you say, oh, there's an imbalance here, right? And that's our imbalance. Oh, this guy here, right, has a height now of 2 versus 1. Oh, no, this is the first imbalance, right? This guy here has a height of 2 versus 1, so he's still happy, right? But this guy here is unhappy because this one is a height 1, 2, 3, while this is only a height of 1, right? So the circled red ones are our 3 problem ones, right? So we turn them into a reasonable tree, right? With the guys hanging below, right? Does that make sense? Are you lost? All right. So
hello, Professor.
I can well imagine that this is on a test.
Dang, still
all
can't
right.
hear me.
So I've certainly had it on tests before. So what would it be before, right? We would start with this tree and we would say, hey, is it an AVL tree, right? And each node can either store the imbalance or the heights. It doesn't really matter. They're the same sort of information, right? So you look at any node here, like node 13. You say, how high are you? You're 2, height 2, and you're at height 1. And the difference is I guess 2 minus 1 is going to be 1, right? This guy here, 3 minus 2 is 1. This guy here is 3 minus 4 is minus 1, right? So you check each node. This node here is 0 minus 0, right? He's a nice 0, right? Everybody check and sees that it's an AVL tree, right? So everybody can do that on the test, right? Then you have to insert 12, right? So how do you insert 12? Is you find where 12 goes, right? So you start at the top and you look at 7 and you say 12 goes to the right of 7, right? So you go to the right of the 7 till you get to 19. And then you go 12 is on the left of 19. 12 is on the left of 13. 12 is on the right of 11. 12 is on the right. Oh, 12 is on the right of 11. That puts it there, right? Everybody follow that? So what you do is you look for 12. And if it's already there, then you can say, hey, you're inserting 12, but it's already there. Do you want to update 12, right? Or maybe you want 2 12s. Then you have to figure out how to deal with that, right? But we're trying to insert it. It's not there, so we put it there, right? There used to be nothing there, and now we put it there, right? Everybody buy that? Can you insert something into one of these trees? Good. So now you say, is it still an AVL tree, right? And which nodes are going to be upset? The only upset ones are going to be the path from the root, right? And so you start at the bottom and find out, are you upset, right? 12's not going to be upset because it has a balance of 0. 11, well, it's not upset, right? You just check. You say, 2, no, 9, are you upset? No, it's 1 here, 2 here. It's not upset, right? 13, are you upset? 13 says, yes, I'm upset because there's 2 over here and 1 over here, right? So then you want to label, oops, sorry. Where did we go? Oh, did I go to the bad button? We did the bad button. All right, so we got, okay, you're following up to see who's upset. And 13's upset. Everybody agree with that? So you circle, you think about these 3 nodes, right? Which nodes are they? The one that was first upset and the 2 that you got to walk in there, right? Those, you could call them, well, 9 is the taller side of 13. Well, why is it the taller side? Well, because you made it bigger, right? And then 11 is the taller side of 9. Why? Because that's the one you made bigger, right? So that's the path coming up, right? Everybody agree with that? And what does that path look like? Well, those 3 nodes, it's going to be a path, but it could be a path that looks like this, or a path that looks like this, or a path that looks like this, or a path that looks like this, right? Now, but anyway, you don't worry about it. You don't have to worry about all these weird cases. We don't want cases, right? We just say we take those 3 nodes, and what do? We say, well, what order do they, let's make them into a balanced tree, right? So that's all we did. We took those 3, the 9, the 13, and 11, and we put them into a balanced tree, right? If you just look at 9, 13, and 11, they're happy, right? They're just the way you want them to be, right? And why did we put the 9 over there? Because it's less, right? You put the smallest one over here, and the middle one here, and the bigger one there, right? You don't have to worry about which way I'm rotating 2 rotations. You just do this, right? Everybody agree? And now, who's hanging off of it? Well, before, there were 4 trees hanging off of it, right? There's 1 tree, 2 trees, 3 trees, 4 trees. Oh, let's see. Oh, yeah, 1, 2. Oh, this whole thing is a tree. 3, 4. Right? People buy that? You see the 4 trees, right? You look at these 3 nodes. Oh, yeah, the red doesn't work very well. And I think maybe we're down to red. All right, let's see how the red works. Right, if I have 3 values, because those are my x, y, and z values, right? We have the values that are here, and the values that are here, and the values that are here, and the values that are here, right? Those are 4 intervals, right? And where are those? That's the tree rooted at 8, the tree rooted here, the tree rooted at 12, and the tree rooted at 15. Right? Everybody see that? These are those 4 trees, right? Because here, what are our nodes? Remember, our nodes are 9, 11, and 13, right? The guys in this tree are all bigger than 13. Yeah? What? Yeah, yeah. And you also know based on the shape, right? Based on the shape, you know that 13's the biggest. Based on the shape, you know that 9's the smallest and 11's the middle guy, right? So you could do it based on shape, or you could do it based on value. It's going to boil down, if it was a good tree, it would boil down to the same, right? Now, if the test was nasty, it wouldn't have the values 13, 9, and 11. So you would have to know from the shape which ones were the biggest ones, right? I'm not sure we're that nasty, but you know, it's possible. So then you would say, from the shape, this guy's the biggest and this guy's the smallest, right? So when you do the rotation, you put this guy over here and this guy, you put the biggest one here and the smallest one here, right? And then you have the 4 subtrees which hang off, right? Everybody see that? And then you say, well, Jeff told me if I do this, it will now be an AVL tree, right? And that's my belief. It's now an AVL tree. And if you're doing it and it's not an AVL tree, then we panic, right? Of course, if I'm given, you know, I'm gonna before I give you a test, I'm gonna do it myself. And if I see that I do it and I don't get an AVL tree, then I'll panic, right? And I'll come back and talk to you about it. But in the meantime, I think this is good, right? Why is it an AVL tree? Well, you just look and you see everybody's going to be happy, right? In fact, it's pretty damn balanced. This guy here has 1 minus 0, so he's a little off balance, but everybody else is perfect, as a 0, right? It became pretty good. Everybody see that? Everybody feel you could do one of these? Right? I mean, sometimes I confess I wonder about you guys. You know, in 1090, I teach them a simple game that's not any harder than this. Why can't people just play the game? You know, it's not that hard. Just do it. All right. Yeah. 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 Yeah, I think so. I think so. When I said your first step was make sure it's an AVL tree, right? That's just so if you're coding this up, it is an AVL tree is the system invariant, right? Remember I talk about loop invariance that you maintain it, right? So we're going to have the fact that somebody's doing an insert operation, and the system invariant is that it's always an AVL tree, all right? So the code wouldn't check that it was an AVL tree. I can just imagine what a test question might be. Question might be, what is the definition of an AVL tree, and is this tree an AVL tree? And you would say it's an AVL tree if for every node, the height of the left minus the height of the right is minus 1, 1, or 1, right? And then they might say, the test question might say, label every node in the tree with 1 minus 1 and, with those. And you would calculate the heights of each and you would do it, right? Or maybe this one didn't use those green numbers. It used the heights. So I don't know which way Jackie goes, right? Boils down to the same, right? And then you should know how to insert, and you should know how to rebalance, right? I think it's doable, right? Or what? Yes, that's what we're doing next, right? And let me tell you right now, deleting's harder, all right? And that's why we're doing it second, right? And again, if the test was nice, it would make you do an insertion because it's easier. If the test was mean, it would make you do a deletion, right? All right, let's go. So here, there's the next page, right? Oh, in fact, I think, look at this. Look at this. Maybe the good news is we're not even covering it, right? Which goes along to maybe it won't be on the test, right? So here, what we should cover, though, is how to do a deletion, all right? Should we review that? Because I think it's kind of fun, and we should know how to do a deletion. Because I can definitely imagine putting this on a test, all right? So here is a tree, and it's just part of the tree, right? The 4 has no left child. If there's no tree drawn there, imagine it's still sitting there. We're just ignoring it, right? Because we're going to have the property that it's always an AVL tree. So this is clearly not an AVL tree, but that's okay. All right? And what are we trying to do? We're trying to delete somebody, right? So suppose who we wanted to delete happened to be 4, right? And what's really nice about 4? Anybody remember? Doesn't have a left child, right? 4 only has 1 child. And why does that make that nice? If you delete 4, right, doesn't have a child, you delete 4, and then you just move it up, right? That was pretty nice. It made this little tree 1 shorter, right? All right, so now that was great, but now we're deleting 3, right? So how do you delete 3? Is you find the node that's the next node in the sequence, right? The guy who's bigger but smaller than everybody else who's bigger, right? And how do you get to him? Well, you want him to be bigger from 3, So you go to the right to 11, right? That's the tree of things that are bigger. And then you want small. Now we want to go small. So you go left, 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 right? Let's see if we do it here, right? And on my assignment, that's all we were doing is we were writing code to go to the next, right? So everybody see how to get the next? You go to 11 because it's bigger, and then you want as small as possible, right? So you go left, 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 right? And see, 4, the guy that you get when you go most left is the number that's next after 3. Everybody buy that? Now, what's great about 4 is 4 doesn't have a left child. Why doesn't it? It's because we went left till we stopped, right? And why did we stop? It's because it didn't have a left child, right? So that means, so that's how we got there. And it doesn't have a left child. So we can delete the 3 and put the 4 there, right? Because it's next. That wasn't a problem. Everybody get that? Now the 4's gone, so we can slide this up, right? People do this? Yeah. Oh, you could have, everything is symmetric. If you look for the guy whose next smaller, then you would have gone left and right, 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 and that would have worked too. And why are we doing it this way? I don't know, because this is the way we're doing it. It would have been symmetric, right? Could work. Now, so it could be that you think, oh, which one would be better? And what AVL, Mr. A and Mr. VL are advising is don't worry about it. Just do this, right? And then, so now we've made the tree one shorter, right? And so that might have made it not an AVL tree anymore, right? So what you're going to do is you're going to walk up the tree looking for the first mistake and then finding those triples and balancing those triples, right? Now, the reason it worked before above was because when we did this, when we inserted and rotated, the tree didn't change heights, right? But here, when you delete and rotate, it fixes the problems here, but it changed, the height might have gotten one smaller. So you have to continue up the tree and find more mistakes and rotate them. So you have to walk all the way up the tree fixing mistakes, but it's still one path up the tree, right? Multiple rotations, right? So now, if you want to ask what's the running time of this deletion, because it's an AVL tree, the height is order log n, right? And so you're finding a path down, you're finding the node, binary search. How long does that take? Log n to find it. And then you have to keep going to find the next guy, right? But that's still finding one path down the tree. So that's all log n. And then you have to walk back up the tree, rotating maybe as you go. But the height, you're just following the path back up, right? So that path back up is still a path of length log n, right? So this whole deletion, you find it, you find the next guy, you swap them, you delete this one, you find the path back up, you rotate on the way back up, all log n time. I think if you just walk by this, right? Everybody good? How are we doing for time? Are we running out of time? 19. All right. Yeah. Yeah. Well, eight might have a lot of children down here too, right? So think about it, this is a big tree, right? And you find the 3, and it's sitting somewhere in the middle of this big tree, right? And now how do you find the guy who's next, right? You go right, left, 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 right? Until you hit an empty tree. So the advantage of 4, right? 8 might have 2 children. 9 might have 2 children. The advantage of 8 is it doesn't have a left child. Oh, no, sorry, the advantage of 4 doesn't have a left child. Do you see why 4 doesn't have a left child? Because we went left till we stopped. Right? Does that answer your question? Yeah? No. No. If you want to delete it, if you're deleting 4, you would say 4 already doesn't have a left. So I just move 6 up, right? The reason we found 3, and 3 had 2 children, right? Yeah. Yeah. So if we were deleting 8, we would just delete it and 4 would move up in its place. Yeah. Yeah. Right? Does that make sense? Everybody good? And if I'm not mistaken, we are done with this topic. All right? Any questions about AVL trees? Yeah. Insert, like here? All the way back? Where are we doing here? Here's insertion. Well, this is insertion. What? Well, the deletion? 4 and 7. Yeah, so here we're inserting 10. When you're balancing. How about I will flip forward and you holler when you want me to stop. Right, so here. So you put 5 in the middle? Yeah. 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 I'm not understanding what you're saying. But so again, so we in this case we came up to the 3 nodes, or the 3, 4, and 7 that you make into a little tree. All right. Right, so here we take nodes 3, 4, and 7 and make them into a tree, and right, so here, this is where our X, Y, and Z, they turn into a tree, and here, the X, Y, and Z turn into a tree. I think those are our 2 examples. I don't know why it said there were 6 examples. All right. So this is just talking about the running time of all these various things, right? If you're doing one kind of local rotation, it's constant time, right? Finding the node, right? You just search for it. Binary search is the height of the tree, but the height of the tree, if it's an AVL tree, is log n, right? Inserting, you have to find it in log n time. Well, and then this says restructuring constant, but you got to go walk back up and find where to rebalance. So I would lie a little bit. I would say that finding where to rebalance takes you log n time, right? And then when you remove a node, you find which one to remove, and then you have to balance all the way back up, right? It's all log n time. All right. All right, so if you know the course sequence of algorithms, we're in 2101, which is data structures, and then there's 3101, which is algorithms. And then there's 4101, which is data structures again. And I've never taught it, partly because my sense of it is that it does a lot of things that I think are dumb. And one of the things I think are dumb is that there are all these types of balanced trees, and they're slightly different, and maybe this one's slightly better at this and one's slightly better at that. But I learned once what a red-black tree was, but we're not going to really cover it here. They cover it in 4101. And then there's a thing called the 2-4 tree. I guess they have, some nodes have 2 children and some have 3 or 4 children, right? And then they have a thing called the splay tree, which quite frankly,